Hello and welcome back to the course on deep learning. Today we're talking about ReLU, which is rectified linear units, and this is an additional step on top of our convolution step. So it's not a separate big step, it's a small step, it's step 1b basically. And what is going on here? Well, we have our input image, we have our convolution layer, which we've discussed, and then on top of that, we're going to apply, wait for it, our favorite rectifier function. And you're already familiar with the rectifier function from the previous section on artificial neural networks. And so sometimes authors or instructors separate the convolution and the rectifier as two separate steps. In our examples, we're just going to consider them just one big step. First the convolution, then the rectifier. And the reason why we're applying the rectifier is because we want to increase non-linearity in our image, or in our network, in our convolutional neural network. And rectifier acts as that filter, or acts as that function which breaks up linearity. And the reason why we want to increase non-linearity in our network is because images themselves are highly nonlinear, especially if you're recognizing different objects next to each other, or just on backgrounds and stuff like that. Like, the image is going to have lots of nonlinear elements, and the transition between pixels, adjacent pixels, is often going to be nonlinear. That's because there's borders, there's different colors, there's different elements in your images. But at the same time, when we're applying a mathematical operation such as convolution running this feature detection to create our feature maps, we risk that we might create something linear, and therefore we need to break up the linearity. So let's have a look at an example. Here is an original image. Now, when we apply a feature detector to this image, we get something like this. So you can see here that black is negative, white is positive values. Well, when you apply a feature detector to a proper image, which has not just zeros and ones, but has lots of different values, and you apply, as we saw previously, feature detectors can have negative values in themselves. Sometimes you'll get negative values. And here, their black ones are negative, white ones are positive. And what a rectified linear unit function does is it removes all the black. Right? Anything below zero turns into zero. And so from this, it turns into this, right? And so it's pretty hard to see what exactly is the benefit in terms of breaking up linearity. I'll try to show an example on this image, but at the end of the day, this is a very mathematical concept, and we would have to go into a lot of math to really explain what is going on. But let's have a look. So for instance, let's look at this building here, right? So this is a building on its own. Then you can see this shadow, this black part, this shadow over here. Well, you can see that it's white, the reflection of the light, and then it's a gray, and then it gets darker, and then it gets darker again, right? So, and when we take it out, we take out that black part. So think of it in terms of linearity, right? So it looks like when you go from white to gray, the next step would be black, right? The next step would be black. It's a linear progression from bright to dark, and therefore this is kind of like a linear situation. When you take out the black, you break up the linearity. Let's try another one. Let's have a look here. And at the same time, it's still that same building, right? It's not like it's not like you're blending two buildings into each other, but that is secondary. The main point is breaking up the linearity. So let's have a look here. Same thing. So you see white, gray, black, gray, white. And when you break it up, you don't have that anymore, right? You don't have that progression, the gradual progression, that you just have like an abrupt change. And that helps introduce non-linearity into your image. It's a very rough explanation, very kind of like on the fingers explanation, rather than technical. But hopefully it kind of helps you understand a bit better what we're talking about here. So here again, you can see white, gray. This is a better example even. You see bright, darker, 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 darker. So this part looks like it's linear. Then you break it up like that. Again, so this is a very rough explanation. It's not absolutely perfect, but at least it gives you some idea of what's going on. But if you'd like to learn more, there's a good paper. As always, there's always a paper. This one is by CCJ Kua from the University of California, and it's called Understanding Convolutional Neural Networks with a Mathematical Model. And basically there he answers two questions, and you need to just look at the first one. And the question is why a nonlinear activation function is essential at the filter output of all intermediate layers. So that kind of explains it in a bit more detail, both in terms of intuition and mostly in terms of mathematics. So that's an interesting paper where you can get some more additional information on this topic. And if you really want to dig in and explore some cool stuff here, then there's another paper that you might be interested in. It's called Delving Deep into Rectifiers Surpassing Human Level Performance on Image and Net Classification. And here the authors, Kai-Ming He and others from Microsoft Research, they propose a different type of rectified linear unit function. They propose the parametric rectified linear unit function, which you see here on the right, and they argue that it delivers better results without sacrificing performance. So interesting read if you'd like to get a bit more into this topic. And that's all for today. The ReLU layer is pretty simple, pretty straightforward, just applying the rectifier function. And I look forward to seeing you next time. Until then, enjoy deep learning.